All right, for 5.6 day 1, we are going to be using imaginary numbers. I believe I mentioned this earlier this week, maybe last week. Does anybody remember what we also could call these instead of imaginary? I just mentioned it kind of in passing. It's okay if you don't. The other term that we use is called complex. So you might hear them called complex numbers instead of imaginary numbers. So if you remember way back to chapter 1, when we first started in August, we classified numbers. Does anybody remember what we always started off classifying numbers as? What was it?
Zero.
Not zero.
Whole numbers.
Nope, more broad than that.
Real.
Real numbers. These are the numbers that are not considered real. So that is part of why they call them imaginary, but complex, I think, is a more accepted term. All right, every number you have ever used so far in this class, at least, is considered to be a real number. Examples of real numbers include 0, -4, 2/3, the square root of 6, 4.5 repeating, 4.264897, and so on and so on and so on. That decimal does not end. Those are all real numbers. However, there is a set of numbers that exist known as the imaginary or complex numbers. The imaginary number is I, lowercase I, and is defined as the square root of -1. So that is super important. I equals the square root of -1. Which means if we take I and square it, remember if you square both sides, squaring and square rooting undo each other. They are inverse operations. So if we take I and square it, we are squaring a square root. Squaring a square root undoes it. So I squared is equal to -1. Correct. So for real numbers, we cannot square root negatives. That's why on one of those homework or practice problems, we said there were no real solutions. Okay, if we're dealing with real numbers, we are not supposed to have a negative under the square root sign. This lesson takes that and kind of throws it out the window. And it's like, well, it's not a real number then. It's an imaginary number. So for 5.6, we're dealing all with imaginary numbers. So for imaginary numbers, it's okay for -1 to be under the radical. Okay, so for any positive real number A, the square root of -A is equal to I times the square root of A. Why? Well, here's why. We can rewrite the square root of -A as the square root of -1 times A. Okay, can we all agree that -A is the same as -1 times A? Okay, that makes sense. So one of our properties of square roots is that we can split the radical up over a product, meaning that the square root of -1 times A is the same as the square root of -1 times the square root of A. It's a property of radicals. You can either combine them with a radical or split them up with a radical. Works both ways. So then, from that last slide, we just talked about the square root of -1 is equal to what letter did we write? I. So that's what they did here. They replaced the square root of -1 with the I. Square root of I times -A. Or sorry, the square root of I times, wow, can't speak. I times the square root of A. It's way harder for me to say than it needed to be. So all they did was break this up into a multiplication problem, split the radical, and then simplify. So that is the reason why. All right, for our first set of examples, we keep it pretty easy. What's special about all these numbers if we ignore? They're negative and they are perfect squares, which makes it nice for us. Okay, so we can, on these, split it up. So we would take the square root of -1 times 4. And then, much like we did on the last screen, we would split that up as the square root of -1 times the square root of 4. And then we can simplify both of these square roots. Are we all okay with what I've written so far? Does that make enough sense to us? Okay, so we just learned that the square root of -1 is I. And we know that the square root of 4 is 2. So we have I times 2. In this case, the radical simplifies out completely. We don't have it at all anymore. Usually we would rewrite this as 2I, kind of like when we have a variable. But remember, I is not a variable. It represents the square root of -1. So 2I is our answer. Hopefully you're seeing this pattern and you don't need to write out every single step. But I'm going to on these first couple ones just so we get the hang of it. I would rewrite this as -1 times 16 so that I can split my radical up. The square root of -1 times the square root of 16. What's the square root of -1? I. And the square root of 16 is 4. So this would be equal to 4I. Questions so far? Can anyone tell me what they think number 3 will equal? 8I. Very good. The same thing happens. Square root of -1 times 64. Split up the radical. And then simplify. I times 8, which we would rewrite as 8I. So for the square root of -256, we would have -1 times 256. Split it up. Square root of 256 is 16, so I'm just going to go ahead and rewrite it as 16I instead of taking that extra step. Okay, so these ones are not perfect squares. So as one of your classmates stated earlier, we are going to have to simplify using the factor tree method. I'm just going to create some space to have a little working room over here and up here, just in case I need it. All right, so on number 5, we could rewrite this as the square root of -1 times 8, which is equal to the square root of -1 times the square root of 8. The square root of -1 simplifies to be I. And the square root of 8 simplifies to be 2 square roots of 2. Now it gets interesting when we have radicals involved with our i's. You can see them written a couple different ways. We could see it as 2 root 2i. Just make sure the I doesn't look like it's underneath the radical. You could even put like parentheses around it or something to separate it from the radical. Or you can put 2I root 2 if you want to. Again, just so that the I is not underneath your radical. Even if you were to leave it as I times 2 root 2, I'd be okay with that too. All right, number 6. Anybody come up with an answer for that one? Perhaps someone I haven't heard from yet today. Jacob? Why don't we take just another minute or two and work through these before we go through them together? Any new volunteers to help me out with number 6? Emily? Sure.
3 root of 5 I.
Very good. 3 root 5 times I. If you wanted to put the I in the middle, you can. It's up to you where you want to put the I. 3 on the outside of the radical, 5 under the radical. The I should also be outside the radical. Number 7, any new volunteers? Sadia. Just the answer is fine. 2 root 3I. Very good. All right. Again, you can put the I in the middle as you want. The I just cannot be underneath the radical. That's the important part there. So for 12, if we needed to see that factor tree, it would be 4 times 3, and 4 breaks into 2 and 2. So that's where we got that pair of 2's, and then the 3 was alone. All right, number 8. Keaton? Very good. 4 root 2 I. Or, of course, you can do 4 I root 2. Whichever you prefer. Again, important part, the I cannot go under the radical. All right, let's talk about number 9 first. So this one I will write out the long way, just so that we can see how this one's a little bit different. So it starts off the same. We split -5 into -1 times 5. And then we split the radical over it. We know that the square root of -1 is I. And then it comes to the square root of 5. Can we take the square root of 5?
No.
Is it going to simplify? No. So it's going to stay the square root of 5. And that's totally fine. Again, if you would rather the I be in the back, you could write it as the square root of 5 times I. You would rather do that. Either one of these is acceptable. I would probably prefer the top one, but really it's a matter of preference. So if it does not simplify, just leave it under a square root. We simplify it by making the -1 part of it an I. All right, let's also do 12 together, and then you can try 10, 11, and 13 on your own. On number 12, what's different about this problem? It's got a number out in front of the square root. So that's fine. That number is just going to kind of come along for the ride. So we've got -1 times 9 under the radical. And then we have the 3 still out in front. The square root of -1 times the square root of 9. This one is nice because the square root of 9 is 3. All of these things are just being multiplied together. So the 3 out in front times, what's the square root of -1? I. Times, we just said the square root of 9 is 3. Which of those things will multiply together nicely? The 3's, right? We're just multiplying this, so we can go ahead and multiply the 3's together. The commutative property allows for that. Multiply in any order. So once we're done multiplying, we just get 9I. So if there is a number out in front of the radical, it just comes along and is getting multiplied to whatever it is that you end up simplifying. All right, number 10. Anybody feel like telling me what they got there? No new takers. City, what'd you get?
5
Good. 5 root 5 times I. Or we could have 5I root 5. It's the same thing. All right, what about 11? Nothing? Well, let's go through it together then. If we're unsure about this.
Wait. Oh. You got it, Sam.
Alexis?
I got 3 times I root 6.
3I root 6 sounds wonderful. Again, the I could go in the back or in the middle. Wherever you want to put the I is okay as long as it's not under the radical. Anybody have something to tell me for number 13? Charles? 40 root what? I don't think that's how that one would work out. What'd you get, Jacob? 30 root 2I. Let's see. 30 root 2I. So if we break down 128, what did we break 128 into?
64 and 2.
What did we break it into? Oh, 64 and 2?
Yeah.
Okay, and then 64 is going to break into what?
32.
Can it break into two numbers that are the same? Okay, 8 and 8. So I'm not sure about this 30. What should it be? Keaton?
40 square root 2 times 5.
Good. This should be a 40. If we've got a pair of 8s, the 8 would get multiplied to the 5. 8 times 5 is going to give us a 40 instead of a 30.
So you can't simplify the 8 down.
Yeah, I thought that you go down to 4 and 4. And then
You can
2
keep
and 2.
simplifying.
Yeah, sure. We can simplify the 8s further. So if we simplify both of those 8s, we get a 4 and a 2, a 2 and a 4, 2 and a 2, a 2 and a 2, right? So we have 1, 2, 3 pairs of 2s. And then that 1, 2 down here that was alone. So what that means is that we've got, 2 times 2 times 2 times 5. Right? Are we all okay with this? 2 times 2 times 2 times 5?
Only 3 2s.
So 2 times 2 is,
4,
times 2 is,
8,
times 5 is 40. The 5 came from out in front.
Oh, so you can't do 2
Why
times.
only 3 2s though? So you only do 3 2s, it's only 3s.
Because we only had 3 pairs. So this one that was alone is the one that stayed inside. So if we're going to break down the 8s, we got to ignore the 8s. Right? If you get a pair of something, even if those two numbers could factor further, you're going to end up with the same number. A pair of 8s is the same as 3 pairs of 2s, because 2 times 2 times 2 still equals 8. Okay, it's just kind of like a shortcut. Questions, concerns about 13?